In my today's lecture, I want to discuss the biofuel energy processes and applications. This is the continuation lecture of the previous lecture on the thermochemical processes. In the previous lecture, I already described direct combustion processes of the thermochemical processes. In my today's lecture, I want to discuss the pyrolysis process and the other thermochemical processes of the thermochemical process. In future, I want to discuss on the biochemical processes and the agrochemical processes. So now come to the pyrolysis. Pyrolysis is called the destructive distillation. The pyrolysis is a general term for all the processes whereby the organic material is heated or partially combusted with the minimal air to produce the secondary fuels and the chemicals products. Biomass pyrolysis is the thermal decomposition of the biomass occurring in the absence of oxygen. It is the fundamental chemical reaction that is the precursor of both the combustion and the gasification processes and occurs naturally in the first 2 seconds. The input may be wood, biomass residues, and the municipal waste or the indeed coal. The products of the biomass pyrolysis include the biochar, bio-oil, and the gases including methane, hydrogen, carbon monoxide, and the carbon dioxide. Depending on the thermal environment and the final temperature, pyrolysis will yield mainly the biochar at the low temperatures, less than 450 degrees centigrade, when the heating rate is quite low, and mainly the gases at the high temperatures, greater than 800 degrees centigrade, with the rapid heating rates. At an intermediate temperature and under the relatively high heating rates, the main product is the bio-oil. Traditional charcoal making is pyrolysis at relatively low temperature with the vapors and gases not collected. The modern equivalent is the torrefaction, but with the effluent gases being burned for heating the process. Gasification is pyrolysis adapted to produce a maximum amount of the secondary fuel gases. Pyrolysis can be performed at relatively small scale and at the remote locations, which enhance the energy density of the biomass resource and reduce the transport and handling cost. Pyrolysis offers the flexible and attractive way of converting solid biomass into an easily stored and transported liquid, which can be successfully used for the production of heat, power, and the chemicals. A wide range of biomass feedstocks can be used in the pyrolysis processes. The pyrolysis process is very dependent on the moisture content of the feedstock, which should be around 10%. The efficiency is measured as the heat of combustion of the secondary fuels produced divided by the heat of combustion of the input biomass as used. Large efficiencies of 80 to 90% can be reached. For instance, the gasifiers from the wood can produce the 80% of the initial energy in the form of the combustible gas, predominantly hydrogen and carbon monoxide producer gas, suitable for operation in the converted petroleum fuel engines. In this way, the overall efficiency of the electricity generation, say 80% into 30%, that is 24%, could be greater than the obtained with a steam boiler. Such gasifiers are potentially useful for the small scale power generation, which is less than 150 kilowatt. At higher moisture contents, the high levels of water are produced, and at the lower levels there is a risk that the process only produces the dust instead of oil. High moisture waste streams such as sludge and meat processing waste require drying before the subjecting to the efficiency and nature of the pyrolysis process is dependent on the particle size of the feedstock. Most of the pyrolysis technologies can only process small particles to a maximum of 2 mm, keeping in view the need for rapid heat transfer through the particle. The demand for small particle size means that the feedstock has to be size reduced before being used for the pyrolysis. Pyrolysis processes can be categorized as slow pyrolysis or the fast pyrolysis. Fast pyrolysis is currently the most widely used pyrolysis system. Slow pyrolysis takes several hours to complete and results in the biocare as the main product. On the other hand, the fast pyrolysis yields 60% bio-oil and takes the seconds of complete pyrolysis. In addition, it gives 20% biochar and the 20% syngas. Various pyrolysis units are shown in the figure. This is the pyrolysis system, small scale pyrolysis unit, and this is the traditional charcoal kiln pyrolysis unit. Vertical top loading devices are usually considered to the best. The fuel products are more convenient, clean and transportable than the original biomass. The chemical products are important as the chemical feedstock for further processes or as directly marketable goods. Partial combustion devices, which are designed to maximize the amount of combustible gas rather than the car or the volatiles, are usually called the gasifiers. The chemical processes in pyrolysis are closely related to similar distillations of the coal to produce the synthetic gases, tars, oils and coke. For instance, the large-scale use of pipe-down gas, just like hydrogen and carbon monoxide in Europe before the change to fossil natural gas, mainly methane, was possible from the reaction of water on heated coal with reduced air supply, just like H2O plus, that is called water plus C is equal to H2 plus CO, and the C plus O2 is equal to CO2, and CO2 plus C is equal to the 2CO. The input materials needs to be graded to remove the excessive non-combustible material, that is soil or metal, dried if necessarily. Usually completely dry material is avoided with the gasifiers, unlike boilers, chopped or shredded and then stored for The air or the fuel ratio during the combustion is a critical parameter affecting both the temperature and the type of the product. Pyrolysis units are most easily operated at the temperature less than 600 degrees centigrade. Increased temperatures of 600 to 1000 degrees centigrade need more sophistication, but more hydrogen will be produced in the gas. At less than 600 degrees centigrade, there are generally 4 stages in the distillation process. Number 1 is 100 to 120 degrees centigrade. The input material dries with the moisture passing up through the bed. Second is the approximately 275 degrees centigrade. The output gases are mainly nitrogen, carbon monoxide, carbon dioxide, acetic acid, and the methanol distillate. Third is the 280 degree to 350 degree centigrade. Exothermic reactions occur in this margin, driving off complex mixtures of the chemicals just like ketones, aldehydes, phenols and esters, carbon dioxide, carbon monoxide, methane, ethylene and hydrogen. Certain catalysts like zinc chloride enable these reactions to occur at lower temperature. Greater than 350 degrees centigrade, all the volatiles are driven up. A larger proportion of hydrogen is formed with the carbon monoxide and the carbon remains as charcoal with the ash residues. With temperatures ranging from 350 degrees centigrade to 550 degrees centigrade, the condensed liquids called tars and the pyroligneous acid may be separated and treated to give the identifiable chemical products just like methanol, acetic acid or the liquid fuel. The pyrolysis yields from the dry wood approximate yields per 1000 kg, that is called 1 ton dry wood for 350 degrees centigrade to 550 degrees centigrade as shown in the table. The charcoal is 300 kg, the gas is 140 meter cube, methyl alcohol is 14 liters, acetic acid is 53 liters, esters 8 liters, acetone 3 liters, wood oil 76 liters and the creosote oil that is the 12 liters and the pitch is 30 kg. Now the pyrolysis destructive distillation, the solid charcoal when the mass yield is 25 to 35% maximum. Modern charcoal retorts operating at about 600 degrees centigrade produce 25 to 35% of the dry matter biomass as charcoal. Traditional earthen kilns usually give the yields closer to 10% since there is a less control. Charcoal is 75 to 85% carbon unless the great care is taken to improve the quality, and the heat of the combustion is about 30 megajoule per kg. Thus, if the charcoal alone is produced from wood, between 15 and 50% of the original chemical energy of the combustion remains. Charcoal is useful as a clean, controllable fuel. Chemical grade charcoal has many uses in the laboratory and the industrial chemical processes. Charcoal is superior to coal products for making the high quality steel. Now the torrefaction. This is a form of pyrolysis at reduced temperature is 200 degrees centigrade to 320 degrees centigrade with the effluent gases being used for the heating. The product is a dry, non-rotting solid car, sometimes called biocoal, that subsequently can be burnt efficiently with the minimum pollution. Biocoal is very suitable for co-firing with the fossil coal in boilers. since it reduces proportionally the unwanted emissions from the fossil coal, including fossil carbon dioxide. Typically, the product retains 80% of the mass and 90% of the heating value of the original biomass. Its characteristics can be improved further by densification. Controlled torrefaction is a relatively new process which is increasing into the widespread use. Now the liquid condensed vapor must yield 30% maximum type pyrolysis. These divide between a sticky phenolic tar that is called creosote and an aqueous liquid that is called pyroligneous acid of mainly acetic acid, methanol maximum 2% and the acetone. The liquids may be either separated or used together as a crude, potentially polluting and carcinogenic fuel with a heat of combustion of about 22 megajoule per kg. The maximum yield corresponds to about 400 liters of combustible liquid per ton of the dry biomass. The liquids are better used as a source of chemicals, but this requires relatively large scale and sophisticated operation. Now the gases must yield 80% maximum in the gasifiers. The mixed gas output with the nitrogen is known as the wood gas, synthesis gas, producer gas, or the water gas, and has a heat of combustion in air 5 to 10 megajoule per kg. It may be used directly in diesel cycle or the spark ignition engines with adjustment of the fuel injector or the carburetor, but extreme care has to be taken to avoid the intake of ash and the condensable vapors. The gas is mainly nitrogen, hydrogen, carbon dioxide with the perhaps small amount of methane and carbon dioxide. The gas may be stored in the gas holders near the atmospheric pressure, but is not conveniently. The much cleaner and more uniform gas may be obtained by gasification or the wet charcoal rather than wood, since the majority of the tars from the original wood have already been removed. The Fischer-Tropsch process is a general term for a wide variety of methods that convert the carbon monoxide and hydrogen, the main gases of the synthesis gas, just like a producer gas, into the well suitable for the vehicle fuel. Open coal has been the starter material used to generate the initial producer gas, but biomass can also be the starter material. Now come to the gasification. The term gasification commonly refers to this high temperature thermochemical conversion with the product gas called the producer gas and involves burning the biomass without sufficient air for the full combustion, but with the enough air to convert the solid biomass with a gaseous fuel. This is the gasifier. The producer gas consists primarily of the carbon monoxide, hydrogen, carbon dioxide and the nitrogen, and has a heating value of 4 to 6 megajoule per nanometer cube, or the 10 to 15% of the heating value of the natural gas. The gasification of the biomass takes place in a restricted supply of the oxygen and occurs through the initial devolatilization of the biomass, combustion of the volatile material and car, and further reduction to the produce a fuel gas rich in carbon monoxide and the hydrogen. This combustible gas has a lower calorific value than the natural gas but can still be used as fuel for boilers, for engines and potentially for combustion turbines after cleaning the gas stream of the tars and the particulates. In the gasifier, first this portion is the wood reduced to charcoal, then the charred wood, then the glowing charcoal. This is the reaction zone here. The air in this side, from this side. Finally the acids come out. Then the hot gas out from the gasifier. Then the gas will be cleaned. Then it will go to the gas filter where the water condensation out. Then the gas will be cooled down and then it will go to the engine compartment. So this is the total construction of the biomass gasifier. The intended use of the gas and the particular characteristics of the particular biomass, that is size, texture, moisture content, determines the design and operating characteristics of the gasifier and associated the equipments. The gas cooling, then the gas cleaning, then it will go to the gas utilization or the engine. If the gasifiers are the air blown, the atmospheric nitrogen dilutes the fuel gas to a level of 10 to 14% that of the calorific value of the natural gas. The oxygen and the steam blown gasifiers produce a gas with a somewhat higher calorific value. Pressurized gasifiers are under development to reduce the physical size of the major equipment items. There are three types of gasifiers are there. One is the updraft, another is the downdraft, and third one is the cross flow. This includes the smaller scale fixed bed updraft, downdraft, and the cross flow gasifiers, as well as the fluidized bed gasifiers are also there. Here the fixed bed updraft, downdraft, and the cross flow gasifiers are shown in the figure. At the small scale, the downdraft gasifiers are noted for their relatively low tar production but are not suitable for the fuels with the low ash melting point. They also require the fuel moisture levels to be controlled within the. Now come to the fixed bed updraft gasifier as shown in the figure. This is the oldest and simplest type of gasifier where the counter current or updraft gasifier shown in the figure. The air intake is at the bottom. This is the air intake, and the gas leaves at the top. This is the exhaust. Near the grate at the bottom, this is the grate. The combustion reactions occur, which are followed by reduction reactions somewhat higher up in the gasifier. This is the reduction zone. In the upper part of the gasifier, the heating and the pyrolysis of the feedstock occur as a result of the heat transfer by forced convection and the radiation from the lower zones. This is the distillation zone and this is the drying zone. The tars and the volatiles produced during this process will be carried in the gas stream. Ashes are removed from the bottom of the gasifier. This is the ash zone from where the ash are collected. Next, the fixed bed updraft. The major advantages of this type of gasifier are its simplicity, high charcoal burnt out, and the internal heat exchange leading to low gas exit temperatures and the high equipment efficiency, as well as the possibility of the operation with many types of feedstock, sawdust, cereal hulls, etc. Major drawbacks result from the possibility of the channeling in the equipment, which can lead to oxygen breakthrough and dangerous explosive situations, and the necessity to install the automatic moving grates, as well as the from the problems associated with the disposal of the tar containing condensates that result from the gas cleaning operations. The latter is of the minor importance if the gas is used for direct heat applications, in which case the tars are simply burned. Now come to the fixed bed downdraft gasifier. A solution to the problem of the tar entrainment in the gas stream has been found by designing the co-current or the downdraft gasifiers, in which primary gasification air is introduced at or above the oxidation zone in the gasifier. The producer gas is removed at the bottom. This is the producer gas in the bottom of the apparatus, so that the fuel and the gas move in the same direction as schematically shown in the figure. This is the air and the gas. On their way down, the acid and the tarry distillation products from the fuel must pass through a glowing bed of charcoal and therefore are converted into the permanent gases: hydrogen, carbon dioxide, carbon monoxide, and the methane. Depending on the temperature of the hot zone and the residence time of the tarry vapors, a more or less complete breakdown of the tars is. The main advantage of the downdraft gasifiers lies in the possibility of producing a tar-free gas suitable for the engine applications. In practice, however, a tar-free gas is seldom if ever achieved over the whole operating range of the equipment. The tar-free operating turn-down ratio of a factor 3 are considered as a standard. A factor of 5-6 is considered for the excellent. Because of the lower level of organic components in the condensate, downdraft gasifiers suffer less from the environmental objections than the updraft gasifiers. But a major drawback of the downdraft equipment lies in its inability to operate on a number of unprocessed fuels. In particular, the fluffy, low-density materials give rise to flow problems, and excessive pressure drop and the solid fuel must be pelletized or the briquetted before use. Downdraft gasifiers also suffer from the problems associated with the high ash content fuels, that is called slag, to a larger extent than the updraft gasifiers. Minor drawbacks of the downdraft system as compared to the updraft are somewhat lower efficiency resulting from the lack of internal heat exchange as well as the lower heating value of the gas. Besides this, the necessity to maintain the uniform high temperatures over a given cross-sectional area makes impractical the use of downdraft gasifiers in a power range above about 350. The fixed bed cross-flow gasifiers. Cross-flow gasifiers, schematically illustrated in the figure, are an adaptation for the use of the charcoal. The charcoal gasification results in very high temperatures, approximately 1500 degrees centigrade and more, in the oxidation zone, which can lead to the material problems. In cross-flow gasifiers, the insulation against these temperatures is provided by the fuel, the charcoal itself. Advantage of the system lie in the very small scale at which it can be operated. Installations below 10 kilowatt can under certain conditions be economically feasible. The reason is very simple: gas cleaning train, which can be employed when using this type of gasifiers in conjunction with the small engines. The disadvantage of the cross-flow gasifiers is their minimal torque converting capabilities and the consequent need for high quality of charcoal. It is because of the uncertainty of the charcoal quality that a number of charcoal gasifiers employ the downdraft principle in order to maintain at least a minimal torque racking. Now this is the summary of the fixed bed gasifiers. The biomass is introduced from the top and moves downward. Oxidizer is introduced at the top and flow downward. Producer gas is extracted at the bottom at the grate level in the downward fixed bed gasifiers. In the updraft, the biomass is introduced from the top and moves downward. Oxidizer is introduced at the bottom and flows upward. Some drying occurs. Producer gas is extracted at the top. This is in the cross flow. The biomass is introduced from the top and moves downward. Oxidizer is introduced at the bottom and flows across the bed. Producer gas is extracted opposite the air nozzle at the grate. The advantage of the downdraft is tars and the particulate in the producer gas are lower. The disadvantage is feed size limits, scale limitations, low heating value gas, moisture sensitive. For the updraft, the advantage is can handle the higher moisture biomass. Higher temperatures can destroy some toxins and slag, minerals and metal. Higher tar content adds to heating value. For the updraft, disadvantage is the feed size limits, high tar yields, scale limitations and the low heating value gas. For the cross flow, the advantage is the simplest of design, stronger circulation in the hot zone, lower temperatures allow the use of the less expensive construction material. Disadvantage is the more complicated to operate, reported issue with the slagging, high levels of the carbon approximate 33% in the ash. Now the second type of gasifier is the fluidized bed gasifier. The operation of the both up and the downdraft gasifiers is influenced by the morphological, physical and chemical properties of the fuel. Problems commonly encountered are the lack of bunker flow, slagging and extreme pressure drop over the gasifier. The design approach aiming at the removal of the above difficulties is the fluidized bed gasifier, illustrated in the figure. Air is blown through a bed of the solid particles at a sufficient velocity to keep these in a state of suspension. The bed is originally externally heated and the feedstock is introduced as soon as a sufficiently high temperature is reached. The fuel particles are introduced at the bottom of the reactor, very quickly mixed with the bed material and almost instantaneously heated up to the bed temperature. As a result of this treatment, the fuel is pyrolyzed very fast, resulting in a component mix with the relatively large amount of gaseous materials. Further gasification and tar conversion reactions occur in the gas phase. Most systems are equipped with an internal cyclone in order to minimize the car blowout as much as possible. Ash particles are also carried out the top of the reactor and have to removed from the gas stream if the gas is used in the engine applications. The major advantage of the fluidized bed gasifiers as reported by Van der Arsen and the others that the steam from their feedstock flexibility resulting from the easy control of the temperature which can be kept below the melting or fusion point of the ash, and their ability to deal with the fluffy and fine-grained materials without the need of the pre-processing. Problems with feeding and instability of the bed and the fly ash sintering in the gas channels can occur with some biomass fuels. Other drawbacks of the fluidized bed gasifier lie in the rather high tar content of the product gas up to 500 mg per meter cube gas, the incomplete carbon burnout, and the poor response to the load changes, particularly because of the control equipment needed to cater for the latter difficulty. Very small fluidized bed gasifiers are not foreseen, and the application range must be tentatively set above 500. The IGCC, one technology that has generated wide interest in the biomass integrated gasification combined cycle technology for the larger scale power and combined heat and power generation in the range of 5 to 100 megawatt per year. An IGCC system involves sizing and drying of the feedstock followed by thermochemical gasification to produce a combustible gas, cooling and cleaning of the gas, and combustion in a gas turbine. Steam is raised using the hot exhaust of the gas turbine to drive a steam turbine that generates the additional power and or delivers the lower pressure steam for heating purposes. The cascading of a gas turbine and a steam turbine in this manner is commonly called a combined cycle. In approximate terms, the IGCC technology will enable the electricity to be made at double or more the efficiency of the steam cycle, and the capital cost per installed kilowatt for commercially mature IGCC units are expected to be lower than for the comparably sized steam. Thus, the overall economics of the biomass-based power generation are expected to be considerably better with an IGCC system than with a steam Rankine system, especially in situations where the biomass fuel is relatively expensive. Generally, these smaller gasification engine systems are targeted towards the isolated areas where the grid connections are either unavailable or unreliable, and so they can be cost competitive in the generating. Further thermochemical processes just like hydrogen reduction, dispersed, shredded or the digested biomass just like a manure is heated in hydrogen to about 600 degrees centigrade under pressure of about 50 atmospheres. Combustible gas, mostly methane and ethane, are produced that may be burned to give about the 6 megajoule per kg of the initial dry material. Second is the hydrogenation with the carbon monoxide and steam. The process is as above, but heating is within an enclosure with the carbon monoxide and steam to about the 400 degrees centigrade and the 50 atmospheres. A synthetic oil is extracted from the resulting products that may be used as a fuel. A catalyst is needed to produce the reactions of the following form: CO plus H2O, that is CO2 plus hydrogen, CnH2ON plus Cn plus 1 H2 produces the NH2O and HCH2NH, where the latter reaction implies the conversion of the carbohydrate material to the hydrocarbon wells. The energy conversion efficiency is about 5%. Third type of thermochemical process is the acid and enzyme hydrolysis. Cellulose is the major constituent, 30 to 50% of the plant dry biomass, and is very resistant to the hydrolysis and hence the fermentation by the microorganisms. Conversion to the sugars which can be fermented is possibly by heating in sulfuric acid or by the action of enzymes, that is called cellulose, of the certain microorganisms. The products may also be used as cattle feed. The methanol liquid fuel. The methanol, a toxic liquid, is made from the catalytic reactions of the hydrogen and carbon dioxide at 330 degrees centigrade and at 150 atmospheric pressure. 2H2 plus CO is equal to CH3OH. The input gases are components of the synthesis gas and may be obtained from the gasification of the biomass. Methanol may be used as a liquid fuel in petroleum spark ignition engines with an energy density of 23 megajoule per kg. It is also used as an anti-knock fuel additive to enhance the octane rating and is potentially a major fuel for the fuel cells. Now the hydrothermal liquefaction, that is called HTL. HTL is a thermochemical process that seeks to initiate at greatly increased speed the processes and turn biomass into the fossil fuels over the geological periods within the crust of the earth. Processes require heating the biomass such as manures, sewage and crops with the water and possibly catalyst to the temperatures 300 degrees centigrade and the pressure 20 to 50 megapascal. At these conditions, the chemical properties of the water vapor, the biomass breaking down into the wells and the residues, the chemistry is varied and complex, and the commercial viability of the well products to compete generally with conventional biofuels already in the market has not. These are the references from which I make my tutorial. So you may go through these references. Thank you.